Good day, process engineers, and welcome to the first process simulation course using AspenHysys. My name is Arias, and I will be guiding you through a practical approach in process modeling. This session is about gas compression loops in early design phases, where the equipment data is not available and the simulation itself is the main basis for the equipment sizing. This schematic represents the gas compression loop to be simulated in this session. The feed stream with the given composition and condition enters a suction cooler, which reduces the temperature before compression. Cooling improves compressor efficiency, allows higher discharge pressures, and also it prevents overtemperature during recirculation. The cooler can be in different locations in the suction site, on the recycle line, also on the discharge site. But the most common one is on the suction site, and the least common one is on after the compressor, because it leads to high settle-out pressures because of high discharge volume. Assignment for this session is simulate according to the schematic and the given information, and also calculate the maximum achievable discharge pressure with the given discharge temperature, the temperature limit, considering 5 degrees centigrade margin. This PFD will be the result of the simulation for today. Opening AspenHysys. Since we have a new case and we are developing a new simulation, we should click New, Create New Case. The first thing I normally do is to save the simulation. The first environment here in AspenHysys when we enter is the properties environment. Here we can define our component list and also the fluid package or property package. According to the feed gas composition, I will add the components. Click on the Add. Here you can see the component list and component database in AspenHysys. You can search it by name, by formula. Carbon dioxide, CO2, water, then the light hydrocarbons. So you can find them here, from methane to normal pentane. Select all and then add. In this simulation, we don't have hypocomponents, but for the future sessions, we will have simulation cases with hypocomponents, and I will let you know how you can create hypocomponents based on the data you have. Now that we have the component list is ready, we can define the fluid package. Click Add the fluid package. For our case, because of the hydrocarbons, by default, you can select Penn-Robinson, but in your project, there might be other recommendations based on the specialist and the evaluation and the experimental data which is done. There might be recommending you to use the other fluid packages. But we are not giving more detail about this at the moment. So we select Penn-Robinson, and our fluid package, including the fluid property and the component list, is ready to enter the simulation environment. In the simulation environment, you have the tools to build the simulation. Additionally, There are two other environments here in AspenHysys: safety analysis and energy analysis. But for using those environments, first you should build a simulation and then use those analyses to do various analyses based on your target. The first thing we do is the material stream, the feed gas. So the blue one is for material stream, and the red one is for energy stream, and yellow one is power. So the information, the condition we have, temperature is 60 degrees centigrade, the unit is correct. Pressure 20 bar gauge, unit is also set, this is what I use. And if the unit was different, you can select that unit and it will convert it with your default unit, which you can set it in your net set. In one session, I will explain with detail and precisely regarding the change of unit and making the unit cell for yourself based on the units you want to work with. Now we can go to the composition, entering the composition. That's, you need to care about what is the basis. Here is the mole fraction. Sometimes you have the composition based on mass fraction or volume fraction. So you need to also take care of that part. Now the composition is defined. And I can go to the condition again. For any stream to be defined, two of these three parameters are needed, the inlet streams. So either vapor fraction, temperature, pressure, two of them. So now here we have the temperature and pressure. And also one of the flow rates. So it can be molar flow, mass flow, standard ideal liquid volumetric flow, or liquid volumetric flow. So any of them, but the most typical one is the molar flow and mass flow. However, in this case, we have the flow rate as standard volumetric flow rate. It's a 6 million standard cubic meter per day, but you cannot have that as an input. So we should use adjust function in AspenHysys to adjust either molar flow or mass flow to reach our target, which is the standard volumetric flow rate of 6 million. So let's bring the adjust function. So you can find the adjust function in the all document. This one is the adjust function, and also you can go to the manipulators. So you can find here all the manipulators, and which most of them should be used in it can be used in steady state environment. So adjust function. How we define the adjust function? Let's click on it. We have an adjusted variable. The variable which will be changed by the adjust function to reach a target value for the target variable. Our adjusted variable can be molar flow or mass flow, and the stream is stream 1. Here I am choosing molar flow. And then target variable is the stream 1 and standard volumetric standard gas flow. The target value is 6 million standard cubic meter per day. The unit is correct. So now, before going to the parameters, I want to show you some, do the example and explain later more about the parameter part. So if I want to start the adjust function, if I click start, it will not start, and I will let you know why. Adjust function is doing an iteration process. So for any iteration, you need to have the initial guess, and based on that initial guess, there will be some iteration calculations, and the matching value will be found based on the parameters we give here, which the main parameter is the tolerance, and also the step size, and also the maximum iterations. If you have small number of iterations, the simulation might ask you many times if you are far from the right number, and also the step size is small. It may take time or many iterations to reach the target value. So what I do here now, I make this one 1000, and then the tolerance, I will make sure the tolerance is small enough for having accurate adjustment. So now it's ready, but still I haven't entered the initial guess. So the adjusted variable was molar flow. The initial guess, you can put any number, likely positive numbers. So I'll just put 20. So now the iteration is finished, and the target value is found based on this tolerance. The tolerance is okay, and most likely the value is correct. So you see standard gas flow, 6 million. So now we define the flow rate. The next step is the feed gas will enter a cooler. So we should go to the heat transfer. You could also select from all of them, but heat transfer is more specifically adding cooler. For attaching the stream, you can hold control on your keyboard and then hold the control and then attach it to the inlet of the cooler. This is one way. The other way is to come to the design tab and connections, and for the inlet stream you can select the stream you want, and it's the same for the outlet and energy streams. You can also type. So for example, the outlet stream is 2, an energy stream 3, but our energy is different, so I'll make it Q100. So now for our cooler to be fully defined, we need 2 parameters. One parameter is the pressure drop across the cooler. So that pressure drop, since we are in a design case and we assume that this is the maximum flow, which results in the maximum pressure drop based on the normal operation. However, the surge condition can be different and the pressure drop can be different. That will be done during later evaluation, but I will put a conservative number at the moment, not a big one and not a large one. Let's say in the design tab parameters, I'll put 0.7. 0.7 bar as the pressure drop for this flow. You know, as flow reduces, the volumetric flow reduces, the pressure drop reduces. As the volumetric flow increases, the pressure drop increases. So now we have the pressure drop defined for the cooler. The next step is to define the temperature, because any cooler and heater, it should know at what extent to do the heat exchange. And providing the heat is typically not the way we do, especially for the cooler and heaters. But in some cases, for example, for fire and some other scenarios, you might need to enter the heat flow. So the temperature we are cooling down to 25 degrees centigrade. So now it is converged. look at the product stream of the cooler. So the inlet stream was fully vapor. It could be also mixture of liquid and vapor, but in this case it was vapor. But after cooling, we have liquid formation, and this is typical. And this liquid cannot be entered to the compressor, which damage the centrifugal axial compressors. Even positive displacement compressors, they cannot tolerate high amount of liquid. So what we do, we should separate that liquid and send only gas to the compressor. So for separating the liquid, I'll go to all. I could go also to the separators, selected, but here also in all, you can bring the separator. And scrubber is typically a vertical separator. For any scrubber, normally, in a common way, we have two, is one vapor and one liquid outlets. In some kind of scrubber, also separators, we can have 3 phases out. So in that condition, we have 2 liquid phases. One is the hydrocarbon liquid, and the other one is aqueous liquid. For the liquid one, in this case, we have a lower pressure in downstream, so only liquid control valve is enough. So the pressure based on the schematic was 12 bar gauge. So I'll put the pressure, and then this part will be, so for the valve, at this stage, that is enough. Later for valve sizing, I will make another session. For heat exchanger sizing, for the cooler sizing, also I will make a session, and the rest. So this session is only about the overall simple simulation of the compression loop. Now the gas stream can enter a compressor outlet, and also we need power. For any compressor to be defined, there are 2 ways. If you have the curve, we can put the curve data here, enable the curves, and let the simulation calculate all the results. In that case, we have to remove the efficiencies given here. But since we don't have any curve and we are in a design phase, then I just let this 75% adiabatic efficiency be stay there. And what else is remaining for the simulation to become wedge is the discharge pressure. We don't know what is the discharge pressure, and also in the schematic, I didn't give you this discharge pressure. But we have one important parameter, is the temperature limit. Based on that temperature limit, we want to find out the maximum achievable discharge pressure. So for that reason, we need to again use the adjust function. So I'm bringing the adjust function. What I'm adjusting is the discharge pressure. I'm adjusting the pressure to set the target value, which is the discharge temperature, to 130 degrees centigrade, which has a 5-degree margin with 135, which was the limit. Stream is number 6. Adjusting pressure. Target is the temperature. Still stream number 6. Temperature. Target value is 130. Unit is okay. Now, you remember, to start the iteration, you need to put the first guess. So, any number, 10. So, still, this number is not correct. This one is by far, it's a wrong number. Because the iteration is not started. So the adjust is not started. And you remember, if you put a small time steps and also small number of iterations, then it will ask you frequently to repeat the iteration. So to avoid this, you can increase the number of iteration here, then let to be solved. So now I want to see if it's correct. The pressure is found, temperature limit was 130, but it did it for 129.9. However, that's acceptable, that's okay, but still, just if you want to be very precise number, then you have to reduce the tolerance. So I reduce it to 0.01. However, you don't need that much accuracy for the temperature, but just for learning purposes. So you see now the pressure respective to that almost 130 degrees centigrade is found. So now we found out the maximum achievable pressure with the condition we have, flow rate and suction pressure and temperatures, and the composition. The last remaining part of the simulation is the anti-surge line. Simply, anti-surge line is the mean flow protection for the dynamic compressors. Here, our compressor, we assume that is either centrifugal or axial. You can also change the direction of the streams, and also the equipment is like acting like a mirror with number 2 of the keyboard. So, and also number 3, it will rotate the stream in the direction you want. So this is the recycle stream, and this one is the flow forward. I'll put a small 0. For the design case, we never put any recycle rate. And the anti-surge valve, holding the control and attaching stream to the valve, and also 2 to just mirror the valve, and also the stream as well. So now we have the anti-surge stream, and we need to connect it here. So for breaking any stream, right click and break. Let's attach it again to show you. Right click, break connection. Now I need to add a mixer. Now we are coming close to an important topic and classic topic in steady state simulations, which is a recycle operation. Here, if I attach to the mixer, it's not solved initially, but just remember, the best way to simulate the mixers is just to define one of the stream pressures and the rest to be identified by the simulation itself. So use equal as all. This is very much more realistic, just to put in the pressures manually and to prevent getting errors. Now it is converged, but this convergence is only for this situation because the flow rate is 0. Since the flow rate was 0, it is matching the flow which is going forward, so it doesn't give any error. But if we change the flow rate, then the simulation goes unconverged. So this can be solved by adding the recycle operation. Recycle operation is, you can find it here. It can be in many locations, but it's very critical for recycle operation. First of all, to limit it, you should have the number of recycles operations that you definitely needed. No additional recycle operations in the simulation, which leads to a good simulation. In addition, the recycle operation should be located in a location that defines the maximum number of variables, and also it prevents unnecessary usage of more recycle operations. Just to simply explain, if I put the recycle operation on this stream, then if I had another recycle stream coming joining here, I should also add another recycle operation for that stream. But if I add the recycle operation here, then any other stream which comes back to this part of the process don't need to have any recycle unit. So what I do now, disconnect this recycle stream, then add the recycle unit here, rotate it, mirror it. Now if I join the stream here, it will converge. So now any changes you do here, the loop will be converged. So there is no issue. So I make it 0 again. One thing to mention, you remember that adjust function was a doing iteration to find the target values, and recycle operation doing the same. So both of them, they require initial guess and later further operation calculations and iterations to match the values based on the tolerance and sensitivity given. So for adjust operation, we had in the parameters tolerance defined, which gives you how exact you get to the target number. And for recycle operation, it is the sensitivity. Let's go to the worksheet of recycle. You need to see if the numbers are matching. The numbers now is exactly matching, but sometimes with this sensitivity we have, you could have slight differences. And these slight differences would later lead to a higher error in the energy and mass balances. So for that reason, it is wise to reduce the sensitivities. For example, to 0.1. Also remember, very low sensitivity values, it can make problems when you are converging your simulations, because it will go to endless calculations and might not find with the given sensitivities. So you can start with the default values, and when you completed your simulation, then you can refine your recycle operations one by one and check, and also you can use the recycle manager. We can discuss about all these topics later in separate sessions, and gradually reducing the sensitivities to make the energy and mass balances with the minimum error. So now our simulation is ready, and I want to go to view and zoom to fit. So here is the task for today. So in the next sessions, there are many topics to follow for the same loop. For example, anti-surge control in the steady state environment, implementing the compressor curve, sizing the liquid level control valve, sizing the heat exchanger or making the datasheet for the heat exchanger, and also datasheet as well for the control valve and the compressor. So all of these topics will be discussed in the next sessions in various parts. In addition, we have anti-surge valve sizing and also settle out calculation for blowdown, cold blowdown, and also settle out calculation for emergency depressurization. So compression loop is a really classic system or classic loop in the process engineering, And if you have a good understanding of the overall loop thermodynamically and also in other aspects like heat transfer and equilibrium wise, and also know the transitions and do a bit work with the dynamic environment, as well as the other evaluations like safety evaluations, it will increase your expertise and it will lead you to be a much better process engineer, and you can use the same experience for all other systems. It's a really classic process engineering loop or system. Thank you very much for attending the video, and let me know if you have any question in the comments, and please subscribe to this channel. I will try to frequently add educational videos that now we started with AspenHysys and later in future with Unisim, Aspen Flare Analyzer, PipeNet, and other softwares. Have a great time ahead.